Yeah, so today I'd like to give a talk that I've called Learning at the Limits. So ML for high performance driving. Today will be kind of a practical perspective on how we can use some of these methods in our pursuit for better control at the limits. So over the past couple of years, the calling card of my team has effectively been autonomous drifting, which looks a little something like this.
John, you're good to go.
Going autonomous.
Temporarily giving an ordinary driver
Whenever you're ready.
the drifting skills of an expert.
Great run.
We use reinforcement learning to do this with an eye towards accelerating the development of some of Toyota's high-performance vehicles. All right, so let's begin. First, I'd like to recognize two of the key people on this work, Frank Jamou and John Gao. Okay, so to begin, we talked a little bit already about what it means to drive at the limits. In practice in vehicle dynamics, what really limits you is the available friction between the tires and the road. Tires have modeling them is really kind of a black art, but at the simplest level, As the tire develops a slip angle, so a deviation between the direction it's traveling and the direction it's heading, generally it develops some lateral force in response to this. Likewise, as there's a deformation in the tire in the longitudinal dynamics, it develops some longitudinal force. These two relationships between the slip and the generated force generally have a very characteristic shape like this. From zero slip, as you increase slip, tire force builds up into a certain peak. So when we talk about driving at the limits, this is actually what we mean. If you then continue to load the tire more by increasing either the slip angle, the longitudinal slip, or some combination, then the behavior of the tire becomes a little bit more variable. So with some tires, like street tires, which are designed to be stable, the tire forces may be relatively consistent. However, with perhaps race tires, you would expect some significant decrease. And so this is actually part of what makes drifting a challenge problem, is as you bring the tire to saturation and beyond, you have some stabilizing force. However, as you cross past that optimal force peak, you're now dealing with an unstable system that you need to stabilize in order to maintain directional stability. But yeah, just to summarize, basically, as you increase the yaw rate of the vehicle or the side slip angle in drifting, the vehicle becomes increasingly unstable. However, it's actually quite hard to model the tire's behavior out in this regime because for a number of factors, aging in tire wear, there's complex coupling between the longitudinal slip and between the suspension dynamics and the behavior of the vehicle. So here, previously, we saw a pure slip cornering case. Here we see a purely longitudinal case. So kind of something to think about is existing models fit the tires only, but still require all sorts of impacts from the vehicle dynamics. So these could include things like normal loads and suspension kinematics. However, in practice, when we're designing controllers for autonomous vehicles, we don't necessarily have access to all of this information. So what this work does is effectively develops a tire model that is able to incorporate some of this information and understand how that correlates with the resulting tire forces. So in practice, what we've done here is learn a relationship between the lateral and longitudinal forces in relation to the lateral slip alpha, longitudinal slip sigma, and then the three vehicle states R, V, and beta. So you might think that if we want to model this relationship as accurately as possible, well, we should choose a neural net and train it through supervised learning, right? It's a simple regression task. Let's build a tire model from the data we've collected. Since we do, in fact, have a pretty good idea of what the tire forces are because we know the vehicle's mass and we can measure its acceleration. That looks a little something like this. So you'll see there's actually two underlying things here. One is the neural network is training and its error is being reduced. The other impact is actually that we're sweeping through a sequence of vehicle states. So even though the blue cloud isn't moving too much, you'll see our approximate tire model is changing very significantly. So as you would expect, the neural network does a fantastic job of fitting the training data. However, it doesn't generalize particularly well. The dashed black line that we see in the middle does not have the characteristic tire curve shape that we would expect. So we can't directly apply this to our model predictive controller and expect to have good generalization results in practice. Instead, we'll find a way to incorporate some of our physics knowledge and some of our empirical expectations about how tire models behave into our model. So as I kind of alluded to earlier, and we'll touch on in a little bit more detail, what we expect in the pure lateral case, which is the simpler of the two, although the combined slip case is roughly analogous, we would expect kind of this characteristic shape in which There's a pronounced steep peak around the origin, and then kind of these plateau-esque regions. So to make this a little bit more formal mathematically, what you effectively would expect is some sort of convex shape at the extreme negative slip, concave shape transitioning to a convex shape around zero slip, followed by a concave shape at very high positive slip ratios. So effectively, we're tracing the tire curve from left to right. One other useful feature might be the ability to control the peak height. So we want a tire model that fits the data well, but at the same time, we want one with the lowest possible peak force estimate. So this allows us to be conservative in estimating the tire's capabilities based on the data we've seen. Okay, so how do we actually incorporate some of that knowledge into our tire model? Well, the approach we've pursued is based on a neural ODE model. What we've done is we've used a neural network that effectively describes a function which we can then integrate twice to get our tire model. So when we're training the neural network, we produce the effectively this function g, which then we can integrate twice to get f, and then we can then compute our loss function. Because of the way we've constructed this and framed this, we know that the function f, our effective tire model, has the required characteristics. We can then train as you typically would in any sort of supervised loss setting. At the same time, we can also enforce two soft constraints on the peak tire forces. All right, let's compare the results we can get with this model to the one we saw with the unstructured multi-layer perceptron. All right. As the model trains, you'll see that the fit to the observed data may not be quite as good as in the pure neural network model, but importantly for the use and control, the tire model itself has the characteristic shape that we would expect as vehicle dynamicists. All right, so this model has a lot of our desired characteristics. It's relatively data efficient, it generalizes, and if we train a distilled version, we can actually apply this on the car. However, there's a number of, they are somewhat difficult to tune in practice because you have to ask yourself, what should the step size be? And what range of alpha do you actually want to enforce these constraints over? So instead, we decided to pursue another solution where we actually limit the expressivity of our model to a class of functions which we know has these desired tire characteristics. So rather than sampling from all possible functions which have these desired properties, we'll choose just one and then parameterize that with a set of neural networks. And that looks a little something like this. We've called this the exponential tan H tire model. Here, the functional form is at the bottom. And it's dependent on these 5 parameters A. We can then learn these. In addition to this smooth curve that is helpful for our optimization algorithms, we can also directly intuit the maximum and minimum of the tire model, which is very useful in predicting the vehicle's limits. Then, to leverage the data that we have to fit these models effectively and keep that model accurate as the vehicle is operating over its full state space, we then make these parameters A functions of a neural network. Again, just as we saw in the neural ODE case, the inputs to the model are our 3 vehicle states. As before, the supervised learning problem looks quite similar. Over our data set, we want to minimize the loss, that is the prediction accuracy of our tire model. And at the same time, we want to be able to enforce some prior belief we have on what the peak tire force is. All right, we can then compare the performance of these 2 learned tire models two empirical tire models that are widely used for vehicle dynamics, simulation, and control. So as we can see, the neural ODE and the exponential tan-H outperform the Pacheco magic formula and the Fiala tire model in prediction accuracy. So as you would expect, through leveraging data, and we're better able to fit the observed behavior of the vehicle. All right, so I've motivated this talk primarily through the question of modeling for control. We've seen that using data, we're better able to model the vehicle's behavior, but what are the benefits in control? So we return to our experimental setting, which is an autonomous Toyota Supra that we call Keisuke. It's guided by real-time kinematic differential GPS, so we have extremely accurate localization information, as well as very rapid updates of both side slip and other velocity states. In the following tests, we'll effectively do a direct swap for the tire model within our vehicle dynamics model. So the Fiala model will come out, and the two learned models will go in instead. And this will be used both for the front tires, which are operating in a pure slip condition, and the rear tires, which are operating in this complex coupled slip regime while drifting. Then we'll run some back-to-back tests. So this data here actually shows the same trajectory we saw in the opening video from my talk. As you can compare, the top plot here is the lateral error, so effectively how well we're tracking our desired path. You can see that the Fiala model in orange generally state the worst case average deviation is 2 meters. However, the two learned neural networks actually do substantially better in this regard. This is important because, as a controls engineer, one of the first things you want to be able to do, even when driving at the limits, is put the car where you want it. Maybe less apparent than in the path tracking, but the next plot down shows our side slip tracking accuracy, so how well we're able to control the degree to which the car gets sideways. And then the third plot shows probably the most important qualitative quantity when you're operating the vehicle, and that's the smoothness of steering. So we want to be able to produce steering commands that we can reliably track with our servo mechanisms on the actual hardware. So anything we can do to slow that down improves our low-level tracking performance and shows a degree of finesse and control in the vehicle. However, due to the model-based nature of our control, we don't just learn models that work well in one scenario. By its very nature, nonlinear model predictive control framework transitions well to different scenarios. So here, we'll see how it performs on a figure-8 trajectory. I also like this video because it really drives home the idea of transitioning rapidly from drift to the left and to the right. If you look closely, you may be able to note the tire marks made by the vehicle over repeated tests. So this gives you some indication of what we mean when we talk about path tracking accuracy. Note, however, that there is more than one figure-8 drawn on the skid pad. So perhaps even more apparent in the figure-8 data than in the slalom trajectory we saw in the previous example, our learned exponential tan-H tire model significantly improves the lateral tracking accuracy. So whereas there's a persistent offset in the Fiala model's experiments, that is effectively much reduced when we're working with the exponential tan-H model. Similarly, when we're operating in the tricky coupled slip region, so this is actually at the end of the test, we're exiting drift and returning to straight ahead driving. We can predict the states more accurately, leading to smoother steering inputs and better side slip tracking over this part of the trajectory. Finally, an additional benefit to using these more accurate tire models for control is that when we make the rapid transitions from drifts to the left and right and vice versa in the figure 8, we see less overshoot in the side slip response. This is important because this is actually the region in this trajectory, at least, when you're most likely to spin out. So anything you can do to predict this behavior accurately means that you can transition to your new target point quickly and safely. Okay, so that will kind of conclude the sampling of the drift work that I want to present and kind of wraps up how we've used some machine learning techniques in actual on-vehicle control with real hardware. Now I'm going to change gears a little bit and talk some about some of our work for driver modeling for motorsports. And I'd like to recognize my collaborators on this work, Jenner Lee, Sean Manuel, and Paul Telkin. All right, so to begin with the question, what do we mean when we talk about driver modeling? Well, our goal here is to predict how a human driver will react and drive in a given situation. However, this situation could be problem specific. So for example, if we're modeling a racing driver in the context of racing, some things we might want would be, as human drivers do, we want to be able to drive the vehicle very near its absolute performance potential. So we need to be able to extract everything out of the tires, kind of as I described in the previous work. However, importantly for this work, since the goal was to use these driver models to actually help optimize vehicle setup in simulation, is that the driver model needs to be able to adapt its driving to changes in the vehicle setup. So as the vehicle's limits change, the policy needs to adapt in such a way that it's still able to get the best performance out of the vehicle. Finally, two other requirements are that one, we may want to be able to emulate the specific style of a driver, at least when we have demonstrations of their driving available. However, an additional requirement that was given to us at the same time was that we still need a driver model that performs well when no such demonstrations are available. So we considered two approaches. Obviously, imitation learning, at least when you have data available, seems like a great way to go because it really learns to imitate the behavior of a specific driver or population of drivers. However, and this is somewhat of a philosophical question, it doesn't necessarily optimize any performance metric. If you talk to most racing drivers, they'll say their goal is to get the car around the track as quickly as possible or to win the race. Imitation learning doesn't necessarily capture this goal. Reinforcement learning instead does. It allows us to optimize the accumulation of a reward signal, and we can tailor that reward in some ways to capture the behavior we want. Also, since we may need to operate in conditions where we don't have any demonstrations, we can generate our own through interacting with simulation. And we can have some confidence that this will help us model the best human drivers because, as was demonstrated by the crew at Sony AI and published in Nature, at least on a single fixed setup, they're able to be the best human or Gran Turismo drivers in the world. All right, to review very quickly, in the reinforcement learning setting, we have an agent that interacts with an environment by taking some action, and in return, at every time step, it gets an observation of the state and a reward signal R. Then through trial and error, your goal is to optimize some policy, pi of s, that maximizes your discounted accumulated reward over the length of the episode. So to get some preliminaries out of the way, we approach this with a distributional soft actor critic framework. And we, I think very importantly for the task of generalizing to different vehicle setups, train it in a multitask setting. When I talk about multitask in this context, what I mean is that given the entire configuration space of the vehicle, so different tires, different suspension settings, ride heights, wing angles, things like that, we train our model over all of these in simulation. Then in terms of reward function and incentivizing the behavior we want in our model, we reward progress around the track, which is our way of saying, go as quickly as you need to, get around the track as quickly as you can, and get to the finish line as quickly. But at the same time, you need to disincentivize certain behavior, such as going out of bounds, excessively scrubbing the tires, heating them up and wearing them, making control inputs that are faster than a human driver could do. And then optionally, and we'll see what this means in terms of imitation, is using a different racing line from human drivers. So to kind of illustrate this, the vehicle state we're using, so this is a low order state capturing the fundamental vehicle dynamics properties, information about the track ahead, and then since I mentioned training in the multitask setting, we also include information about the setting itself. So what this allows us to do is condition the policy on the vehicle setup. So the agent can then drive in a way that is, it can effectively anticipate the vehicle's behavior rather than simply react to it. Then the outputs of our policy are steering angle, throttle pedal, and brakes inputs. Really quickly, I'd like to introduce two notions of imitation when we talk about imitating human drivers. So the first would be taking the same action as a human driver was observed to in a given state. And we found that we can actually do this pretty easily by augmenting the policy update with a simple behavioral cloning loss. Perhaps more important, especially as the vehicle setup changes, is that we want to be able to visit the same states. However, we can't use all states for this, because as the vehicle's performance limits change, you may use the same racing line, but you may have to drive faster or slower to get the best performance out of the car. So in this case, the incentive was really just to use the same racing line. And we found empirically that the second goal actually helps us improve lap time slightly, as we'll see in the following example, while the first goal had a small negative impact on lap time. All right, to bring me to the experimental results of this work, what we did was we just devised a kind of a battery of 4 different tests. So each of these are a high fidelity multi-body simulation model of the Lexus RCF GT3 car driven around Fuji Speedway. We gave these 4 setups to a professional human driver and had them set the best time they could in a motion simulator. So high fidelity motion base, surround screen, all that good stuff. Then, without looking at any of their data, we trained a policy to see how fast it could go with these 4 setups. And we actually found that we were able to outpace the human driver. And importantly, for the question of vehicle setup optimization, we maintained the general trend in lap times. So we saw on this slide how much the lap times vary. So maybe about 2 seconds in total from the fastest setup to the slowest setup. Actually, just slightly less than 2 seconds. So this next couple plots, we'll see how the agent actually adapts its driving to these various setups. And maybe for context, let me just give you a little bit more on how these setups were devised. So we have a baseline, and then an understeer setup where you'll have effectively less peak tire front grip. So this is a stable car, easy to drive, but not as fast. Oversteer, where you have less rear grip. This is a tricky car, liable to spin out. And then we effectively have just the baseline setup, but with an equal increase in grip compared to each of the 2 cases. So comparing the 4 trajectories, we don't see significant differences across the whole lap. So this is actually interesting, and I think, depending on who you ask, may or may not be consistent with what human drivers do. I think more interestingly is that most of the difference in lap time actually comes from differences in the driven speed. And importantly, for the use of consistent exploitation of the vehicle's performance potential, we found that these speed traces don't really cross. When you're driving the setup that we expect to be fastest, because it has the most grip, it is in fact fastest everywhere. Similarly, much like human drivers, the steering inputs that are actually made to the car differ. So in green, we see the oversteer case, and we see these necessary corrections that are used to maintain directional stability of the car. They're here. These are these kind of downward spikes as the driver model straightens the wheel to avoid a spin out. And finally, to kind of drive the point home, while it's a subtle difference, you can actually see that the driver model is in fact exploiting these differences in performance because the accelerations the driver model achieves as it drives around the track actually vary directly with the amount of grip available. So this is exactly what we would expect. Okay, so I'll conclude with a video. What this is a simple animation of the trajectories driven by the human driver and by the driver model in two settings. So the human is in green, you'll see a population of their laps, and then you'll see in blue our RL agent that was trained without any knowledge of the human behavior. On top of that, you'll see a red agent, which is, in addition to the cost function I described earlier, incentivized to use a racing line close to the average of the human demonstrations. This is playing in real time, so the lap time is about 1.5 minutes. So as you come down the main straightaway at Fuji, it's one of the longest in the world from what I understand. You brake for the first corner, and you could already see differences, slight differences in the racing line used by the human and the various agents. So note while the red and blue agents are neck and neck at this point, they generally take different approaches to each corner, with the blue agent diving in a little bit earlier, drawing ahead in the early part of the trajectory, only to give most of that gain back in the latter part of the corner. Note too how the path of the red agent is pretty close to the center of the human lap distribution. We're coming into the last corner, blue is ahead, but red takes the day with superior exit speed onto the final corner. So I think what we can take away from this is that humans, as impressive as what the RL agent can do in terms of vehicle control, humans really do have better insight into what it means to take the best racing lines. There may, in fact, I think I will acknowledge here quickly that could be a few things the RL agent is exploiting. Since this is simulation where human drivers are very good, it is not the same as the real world environment where they spend most of their time. So our agent could be exploiting something that the human driver isn't willing to do in the real world, and so is therefore not willing to do in the sim. Okay, I'd like to conclude my talk with just two final thoughts for you. The first is that whether through model-based control, as we saw in the MPC work, or the model-free reinforcement learning, ML has a lot to offer us in the study of high-performance driving. However, we've found, whether through incorporating side information into the tire model or human demonstrations into the driver model, incorporating expert knowledge is in fact key to getting the best results. All right, with that, I'll take any questions.
Hi, thanks for the talk. I had a question about your RL setup. You noted when we were watching that video that the RL agent without the behavioral cloning objective tends to dive into the corner faster, but then sacrifice exit speed. And I was curious, like when you're training this agent, are you using like a dense reward? And like, if so, does the discount factor of that reward sort of impact the behaviors you're seeing?
Yeah, great question. We are in fact using a dense reward, incentivizing progress along the track at each time step. However, we found that within the practical range for that discount factor, we haven't been able to get policies that work well, or we haven't necessarily been able to increase the effective horizon over which the policy effectively plans by increasing that discount factor. So I think in some sense we are kind of just limited by the fundamental performance of the algorithm there.
Yeah, thanks for the talk, John. I was wondering, so like in terms of I forget if it was the red or the blue that incorporated the racing line information from the human. Is there any other ways that you've been looking at incorporating information from what the human did? So for example, I assume that doesn't have the velocity information or the steering information. It's just the trajectory. Is that right? And is that generally the best thing? Like, is that generally the kind of biggest help we can give the model, or is there other aspects we can give? And just to follow up to that, did that help training time? Did it train a lot? Like, was it less iterations to kind of get to a good policy with that? The hint of, you know, what constitutes good racing?
Yeah, two fantastic questions. I think I'll start with the second because it's slightly easier to answer. Yes, we found it did improve training performance to get to a certain level. However, you know, I think at best, you know, this is somewhat less than a factor of 2 improvement. So it wasn't necessarily like a tenfold increase.
Yeah.
I think in terms of future explorations, or, you know, if we were to continue heavily with this work, I think other things that we might look at incorporating would be, so I think we've looked at this with some success, I think, just in terms of incentivizing exploration around the human trajectories, even like very simple potential-based reward shaping. So we have some initial experiments that suggest that this works well when you have at least one human demonstration.
Yeah.
You don't necessarily get the behavior we observed where the agent will follow the human racing line. But, you know, where it's beneficial, it does leverage that.
Yep.
The other piece I think is something I think is slightly different from what you asked, but maybe potentially quite interesting, is really just, since we've designed the reward function by hand to incorporate information about which we know from talking to human drivers and to race engineers that these are the things they think about. But that's only true kind of up to a scaling factor, right? We don't know necessarily the correct weighting between tire slip angle and progress, right? And so there, I think we could do, you know, there would be an easy extension to incorporate to more accurately capture human driving behavior if we tried to make that trade-off in the way they do. So effectively, like tuning the weights and reward function.
Yeah, and related to that, beyond the humans themselves, is there any other kind of priors we can put in? So like, I guess in the first part of your talk, you were talking about these neural ODEs, that, you know, the way in which you kind of, you know, architect that as opposed to just, you know, throwing a kind of a fully layered kind of network at it, really helped it out. Is there any other kind of, you know, beyond second order ODEs, is there any other kind of like interesting prior information, again, not necessarily to do with human racing, but more to do with physics, that could help out the training?
That's yeah, I think I'll answer the question in 2 parts. Like I think we have a pretty good idea from vehicle dynamics about how to select the state information to make available to the agent. At the same time, part of the interesting part that we don't necessarily get to leverage on the drift car is that we have much better knowledge of how the simulation functions.
Yep.
So if the goal is to operate at the tire peaks, like that information is actually available to us in the sim.
Yeah.
Like we know exactly where that information is. So if we want to design an agent that can adapt broadly or in very few attempts to a new setting, it might be possible to leverage some of that ground truth information about tire saturation.
Yeah. Okay, cool. Thanks. And we might have some questions online. Is that Joseph or online?
Let me see if I can get it up on screen. Oh, yeah. So the question is, do you think the recent trend in LLMs will have implications in the autonomous racing field? If so, what aspects or in what way do you envision that LLMs might enhance the performance of controlling vehicles in such extreme situations? So I think this is really highly speculative answer, but I think, as a first pass, we could look at automating some of the ways human beings talk about vehicles. So I think some things we could do here are, after a driver goes out and tests a vehicle setup, he goes back and talks with his engineer and says, this is the way the car is handling. He describes it in words. I think what would be very interesting is if you could have a similar concept for the vehicle setup optimization itself. So if the agent could not only drive the vehicle, but based on how it behaves in simulation, come up with some relatively succinct way of describing how that would feel to a human driver. Because, it's not necessarily about just having the fastest car. It's about, having the fastest car the driver is happy with. So I think that could be something that's really interesting. Or you could go the other way. And if you have, information about how a car behaves based on driver input, you could condition the policy on that, perhaps. So I think both of those would be super interesting.
I've got two questions, pretty unrelated to each other. The first question is the tire model section. The first, or all the data seem pretty noisy. Is there any value to incorporating uncertainty into the model that you fit? And then the second question is, you mentioned that you have a dense reward for progress for the human driver modeling. Since you're doing it in sim, can you just make it sparse, just make the reward lap time? And if not, why not?
Yeah, good question. So the first one is noise in the data and incorporating uncertainty. So I think yes, your thinking along these lines is very close to our thinking along these lines. And I think this is going to be a huge research thrust, not just for this epistemic uncertainty, kind of the noise you're seeing in data, but actually more fundamental. Like if I don't know what tires I'm on, or if I could give you like a set of tires from a population and say, go drive fast, or on a surface you haven't seen before, how do you drive at the limit or close to it safely? So I think this is exactly the research question we're delving into now, and I'm pretty optimistic we'll have some cool results in the next year and a half, something like that. I think your other question is a good one. I don't necessarily have an answer for you, apart from maybe asking the community to consider, if you think these problems are cool, maybe think about what sort of approach you would need to leverage in a planning horizon, or over a lap and a half, or 5 or 10 laps of a race, for example.
Cool, thanks.